Hi, Micah. Come on in, everyone. All right. Well, it's well after time to start class. I don't have very many people here, but I really need to get started. What I want you to do is we are now starting chapter 22, and I need to get you on the mindset of thinking about something called electric flux so I can introduce you to Gauss's law. So if you imagine uh, a window, mhm. So imagine trying to, let's say, let light go in through a window, or let's imagine it being a hole in the ceiling. Doesn't have to be a window, in other words, a rectangular hole in the ceiling, and you want to basically throw. What you doing in here, Chase? You want to basically pour things through that hole in the ceiling, but the ceiling has a grate on it. So imagine it almost like screen. You know how screen looks like you have screen on a screened-in porch. Well, imagine if you had a grate over the hole in the roof, and the grate was like this thick, and it had big square holes through it so that you really had to pass straight through to get in. If you then tried to shine light at any other angle other than straight down, or if you then tried to pour flour through any other angle other than straight down, or if you tried to allow marbles to fall in through the grates at any other angle than straight down, uh, by tilting it and making it go at an angle other than straight down, that path through that screen type mesh would actually prevent some of it through getting through. That's sort of like what flux is. When we talk about electric flux, we only care about the portion of the electric field going through a hole, say, that is actually perpendicular to the hole. Okay. And so the hole is like this or like this, and just like before, we were trying to take this hole that had this screen thing over it, and we were imagining flour, light, marbles, whatever going through, and it had that special grate on it where it had long rectangular holes through there. And if you happen to shoot a marble at this angle, there's some probability that it would actually hit inside of a hole and then bounce to the other side of the hole, and then bounce to the other side of the hole, and then bounce it, and then make it through. But that's a lot lower probability than the marble just falling straight through because it happens to be parallel to the path of the little hole. So what we want to do is take into account when electric fields are doing that within certain areas, which you can picture as windows as well. So let me draw a drawing. Again, I'm not going to take the time. I was actually when I was waiting for you guys to come in, I was actually drawing a rectangular grid like screen, and I was going to draw it in 3D, and it just it was not fun. So, anyways, now that I have that idea, hopefully you guys can get it. So if you look and say, let's say we take a window that looks like this. Okay. And I'm drawing it in 3 dimensions. So uh, basically, it's just a vertical wall like the left wall in a room. And what I'm
Oh, are you
saying,
sharing your screen?
no, I'm not because I'm
Okay.
very, very smart that way.
I was about to ask the same thing.
Thanks again for helping me. I get so excited. I'm just so excited. Have y'all heard Kevin Hart do that? I'm so excited. Oh my God, it's so bad. All right. So, yes, I'm sharing the screen. Well, I'm attempting to share the screen now. So if you imagine that this hole in a wall is like a hole in a wall in the left side of a room, then you could imagine light or electric field lines or stuff like that coming straight through. And because of this, because they're all exactly horizontal, they're all going to go through without deflection and without loss, even if I had that fancy grate thing that I was talking about. Okay. So that, for instance, is that line. Then there'd be another line here, another line here, another line here, another line here. And all this would go through undeflected, even with the grate in there. Now, if you change it up a little bit and say, let's keep that same window. So we're going to keep the same window now. And I'm going to say the window is like this. I'm going to say this window is like this. But now, instead of my rays going perpendicular to that window like they did in the red case before, and really I should extend these just a little bit more, just to show that they're in fact the same length. If I wanted to, I could imagine these rays coming at an angle other than perpendicular. So what I'm going to do is draw these blue lines to represent perpendicular. So that's what the light, that's the way the rays were coming in before, is they were all coming in perpendicular to the surface. But I'm not doing that now. I'm going to have you consider a case where they're not going through perpendicular. They're going through, in fact, at a slightly different angle. And that just allows me to see exactly what that angle is. So what I'm going to do now is say, all right, now all of these are coming through this at this angle like this. Okay. So they're all now trying to come through at an angle. But to be honest with you, because of the problems of that grate being in there, we know that you're not necessarily going to get very much of these lines coming through, specifically because a lot of them are going to hit the grate and be deflected. So if you called this angle theta, notice that that angle is the same for all of them, okay? Then you could actually represent this area, which I'm going to say is this area right here, drawn by, I don't know why I chose blue since I already had blue up there, but anyways, I did it. You could represent the area of this window by a vector. That's just a unique tool you might wish to use. And that area vector, which is, as you can see here, is clearly perpendicular to the actual window, okay? And you could make its length equal to the area. So for instance, if this side had a length A and this side had a length b, the magnitude of this would be a times b, but it would be a vector, and let's say it's pointing in the n hat direction where n is normal to that thing, okay? So if you let yourself define a vector to represent an area of a hole, that's a way you could do it. Now, there's no clear way to say that the A is going to point that way versus, say, the A vector pointing this way. Okay. Later, I'll introduce something that allows us to do that, but you could do it either way, and it wouldn't matter too terribly much either way. Okay. So right now, if you're just trying to imagine light or electric field lines or magnetic field lines or gravitational lines going through an aperture whose width is A and whose height is B, then what you could do is imagine a vector perpendicular to that window whose magnitude is actually equal to the area of that window, i.e., A times B. And you could say the amount of light or electric field or magnetic field or gravitational force or whatever you're counting, you could say that that amount that got through is called the flux. And you could define it to be a vector dotted with in this case, I'm going to call these red lines my electric field, like that. So I'm going to say it could be A dot E, because notice A dot E means the magnitude of A times the magnitude of B times the cosine of the angle between them. And if you'll notice, your vector, here's a small diagram of it, your vector looked like this, where this is, excuse me, I actually should have drawn it the other way. No, that's cool. Where this vector right here is the electric field vector. This angle right here is the angle theta, and this vector right here is the A. Okay. Now we know that the area is just A times B. We know the magnetic field strength is E. And if we take the cosine of theta, which is the angle between them when they're tail to tail, what we see is we're getting the component of E that is parallel to A. So when I zoom in right here, what you're going to get from multiplying A times E times the cosine of theta is just this little part. This is A. Well, I'll make it a little bigger. This is A times E times the cosine of theta. Does that make sense to everyone? So notice the A times cosine theta. Let me write it in a different order. Maybe that'll help. Uh, I'm going to write the E first. And actually, no, I'm going to write the A first. So A and then times E times cosine theta. Notice this is exactly equal to that little part right there, right? So if I took E and multiplied it by the cosine of theta, it would actually be technically a little bit further than that. It would go like this, okay? And then that would be actually correct to draw that way. Okay. So do you see, by doing that little dot product thing, we can pick the parts of the electric field that are actually perpendicular to the hole in some sense. And again, perpendicular to the hole means really kind of parallel to the hole. But what we're doing is representing parallel to the hole by something that's perpendicular to the glass that would fill it in. So that's what flux is we want to think of taking a vector, like in this case, the electric field vector, and having it do a dot product with a normal vector, and that normal vector represents the area of the actual hole, and it's actually perpendicular, or in some sense parallel or perpendicular to the hole, whichever way you want to see it. And that's what flux is. It turns out this flux, which is the electric flux, is important. And later, when we start studying magnetism, flux is going to be important there too. So we'll have another flux called magnetism, okay, or the magnetic flux. So has everybody got an idea what I mean by taking the electric flux or calculating electric flux? Now, I don't see anybody typing anything. Let me put up my chat just to make sure. It does not look like anybody. I just now seeing Micah's response to me earlier. Uh, so I don't see anybody post anything that concerns them. So that's what the flux is. Now, if it gets more complicated than that, what if, for instance, instead of having a nice flat window, what happens if you've got a little piece of area like this, say, that can have a very different shape. And in fact, at this particular point, it might have an electric field that points this way. And then at this particular point, it might have an electric field that points this way, and so on and so forth. What do you do then? Well, what you do then is you divide this up in as small of pieces as necessary that will allow you to basically say, okay, over all these small pieces, I've gotten them so small that the individual electric field vectors are essentially a constant over every single one of these itty bitty areas. Okay. So now what you can do is you can look and say, okay, well, I got this little itty bitty area, which might be, let's say, this one right here. Okay. And at that particular spot, what I find is the electric field points this way. Okay. And the actual area vector for and I'll do this one in green this time, the area vector for this little particular area is going to be like this. And let's say this is X and this is Y, then dA would equal X times Y times N hat. In other words, again, I've chosen a vector that's normal to that itty bitty surface, and I've chosen a unit vector so that its magnitude won't mess up the size of dA. And dA, in fact, has a size equal to the area. So you can see this angle right here is theta. And then again, you get the flux is equal to E. And I'd say the flux for that little differential area is E times dA. Does that make sense? That we could, take a rather rather violently changing surface with a rapidly changing electric field over top of it, and we could dice it up smaller and smaller until finally one little area of that box of that violently changing surface is completely flat, and the electric field covers such a small angle or such a small area over that little side that the electric field's essentially constant on that. And then we could take the dot product of that particular electric field at that particular rectangle and get the flux for that particular rectangular part. And then we could add them all up. If we do that, then we get the modern definition of the electric flux, and that is it's given the capital phi, the Greek capital phi, It's often subscripted E just to remind us that it's electric field, not the electric flux, not the magnetic flux. And the general result is it's going to be the integral of E dotted with dA. Okay, does that make sense? Do y'all see how that's a logical extension to what I drew at the very top? All right. Well, I promised you that I would remedy the situation where I had the green arrow and the blue arrow both representing the area of the little hole up at the top. So now I'm going to do that. If you actually have a closed surface, okay, that means one that has a clear inside and outside. Let's say one that looks like this kidney bean shape right here, say. Whoa. Okay. So that was just horrible. So that has a clear inside and outside. And you can probably tell it by looking at these lines on it. It gives you somewhat of a shape to consider it to be in. And in fact, you might even consider this line like that. And another line like that. And let's say maybe one more line like that. Okay. That has a clear inside and outside. And you can tell it because if you put something in the inside, there's no way to move it from the outside without crossing the surface. Because of that, this gives us a unique opportunity. If we restrict our attention to closed surfaces, then we can arbitrarily choose the dA vectors that that point out of the closed surface. So we had the ability to choose the ones that point into the closed surface or the ones that point out of the closed surface, but that's really the only two choices we had. What's been done is we have chosen to point the differential area vector out of the surface. So in this case, that would be your dA vector right there. Okay. And over here, for instance, your dA vector would be this one. Okay. And over here, that would be your dA vector there. Does that make sense to everyone? Now, it turns out that is an arbitrary definition, but it turns out to be a very good definition because Gauss's law, which by the way is called Gauss's law, not Gauss's friendly tip that sometimes works. It is called Gauss's law, and I'm going to come back to that being called that way for later on. But the main thing is it is a law, and because of it, and because of our way of defining that, it turns out that Gauss's law wouldn't have much importance except in the case of closed surfaces. So yeah, we did that mathematically to have a definitive way to say whether the flux would be positive or negative, because if we flip one side to the other, that's really the only difference, is whether the E dot dA is going to be positive or negative. So let me start with a very simple example of calculating the flux. When I say very simple, it's actually the simple ones are ones like I shown here, where if theta was 60 degrees, you'd have to hit cosine 60 and then multiply that by, either newtons per coulomb, which is one unit of the electric field, or volts per meter, which is another unit of the electric field. And that would be cosine 60 times the newtons per coulomb, and then times the area. So it'd be newtons per coulomb times meter squared, with meter squared on the top. That's the actual units of the flux. Okay. So the simplest case, like I said, is a nice flat surface. You just take the magnitude of the electric field, you multiply it by the area, and then you multiply that by the cosine of the angle between them. That's the simplest case. Your book does 2 or 3 examples like that. I'm going to take a bigger one, and we're going to, in general, learn something bigger too. We're going to learn a surface integral, and that's what I was talking about here. By integrating over these surfaces, I'm actually creating surface integrals, which is a whole nother branch of our portion of Calc 3 that you sometimes get to. But to be honest with you, I've never been, when I was at Chapel Hill, when I was at NC State, when I was at East Carolina, none of them ever really got to that section on Calc 3. So it's not something that you necessarily have. But the good news is you learn it from your physics or your engineering instructors. So let's imagine coordinate system. So I'm first off going to draw a little coordinate system here. Okay. I'm going to call this axis pointing out of the page is the positive x-axis. I'm going to call this axis pointing to the right into the page, or in the page. It lies in the page, in other words, and pointing to the right, that's the y-axis. And the axis that lies in the page and points up is the z-axis. Okay. So I'm going to also endow this axis, or this coordinate system, with a point charge Q at the center. So consider a point charge Q at the origin. Okay. Now, it's a charged positive Q. I would like to know if I go 3 squares over here on the y-axis. Oh, I should do that in a different color. Let's go. If I go 3 squares over here to the right, in which direction will the electric field point as a result of that charge Q? Okay, so there's the question I just asked. Anybody have an idea? I've drawn one green dot so far, so I want to know in what direction will the electric field point at that green dot right there. Not getting the quick responses I expected, so I'm going to give you a reminder. The electric field always points the direction that a positive charge would be compelled to go if it was in that electric field. So I've got a positive charge sitting there at the origin, and I move to the right of it 3 squares. And if I put a positive charge there, which way would that positive charge at the green dot tend to try to run? And you can just speak out if you want. or you can type it if you don't have speaker working. Anyone? Let me answer this one and see if y'all can get the next one saved. Whoa, Nelly. I'm drawing the vector purple, and I made it 1 square long. Okay. Now let's draw another green dot. And again, let's put it about 3. Actually, that's a little too far. Let's put it about 3 squares back along the negative x-axis. So which direction will the electric field point at that green dot? Anyone?
Would it be away from the origin?
Exactly, away from the origin. And notice it's 3 squares away, so it should be about the same strength as the last one. All right, how about, seems like you're getting it now, so let's try this one on the left. Which direction will the electric field point?
To the left.
To the left, very good. Okay. And how about now if I do another green dot right out here in front, which way will the electric field point there?
Down and to the left.
Yeah, but remember this is 3 dimensions and that X would be pointing out at us. So it would literally be pointing directly at us.
Yeah.
Okay. But yeah, you're right. You're drawing it along the axis. And notice they're all the same length because they're all the same distance away. And we know the electric field E is equal to, at least in magnitude, Q over 4 pi epsilon naught r squared, where r is the distance from Q to the point at which you wish to know the magnetic field. Let's try another one. Right about there. And let's try another one right about there. Where's the electric field for that top one going to point? In which direction? Anybody else? You can still give it another try. Whoever answered me last time, it's fine. Doesn't seem like too many people were interested in answering it.
Positive z-axis.
Yes, in the positive z direction. And again, it's 3 units away, so it'll be the same strength. What about that bottom one? Anyone?
The negative z-axis.
Exactly. Okay, so what I'm doing here is I'm trying to see from what you've learned about electric fields, can you tell me of a surface that I could create around this charge Q that everywhere on the surface, the electric field would be perpendicular to the surface and it would be constant on that surface? Can you tell me what kind of surface I would have to surround that thing by? So we're looking for a surface that 3 meters to the right of the point charge would have a surface that is obviously perpendicular to that purple vector, which means it'd be parallel to the XZ plane. Similarly, on the left-hand side, that one would be parallel to the XY plane, excuse me, the XZ plane, at least at that particular itty-bitty green spot. Okay. So
Carly said a sphere.
a sphere would be a good, oh yeah, thanks, Carly. Yes, that's exactly right. It is a sphere. And in fact, if you drew a sphere without erasing it, like I just keep doing, okay, the sphere would look something like that. Of course, I tried to get this thing to draw it properly for me. Okay, so there's the actual sphere. And in fact, the actual sphere would be a obviously 3-dimensional sphere like that. And then, of course, like this as well. So that's basically the shape. And this is the big part of Gauss's law. What you have to do to use Gauss's law in the form that we're getting ready to use it is, and here's Gauss's law, by the way. Gauss's law says that the flux, dang it, I'm gonna draw pretty stuff. It says that the electric flux over any closed surface. So notice I'm going to write that integral, but this time I wrote an integral with a circle on it. That circle is just to remind us, hey, this equation that I'm attached to doesn't apply unless you're applying it to a closed surface. So the electric flux through any closed surface is going to equal something very specific. I'm getting ready to derive what that is, but I wanted to show you that part. So what we're going to ultimately do is we're going to have a right-hand side to the right of that equals. That is something very simple to do. And now I'm going to use that to actually calculate what the net electric flux exiting that sphere will be. Okay. So what I can do is I can say the closed integral of E dot dA is equal to, now what we've noticed is that the electric field points radially outward. That's why I was getting you to draw those little purple arrows. They all point radially outward. In other words, if you traced the arrow backwards, they would all converge right at the origin. That means they're radial lines, and radial lines can be represented, at least in spherical coordinates, by something called the r hat vector. Okay. If you would like to know more about the coordinates, I'm just going to use these symbols from time to time. But if you would like to know more about those coordinates, which you will eventually learn, you can just look in day 0 of my Canvas page, and you'll see I introduce you to the spherical coordinates and to cylindrical coordinates. All right. So what this is going to become is an integral of the electric field. What you guys know is the electric field is Q over 4 pi epsilon naught r squared. So if I said the radius of this sphere of radius r, if I said that's the radius, then the electric field on any particular spot, let's say I'm going to choose this spot right here. Well, I'm going to choose this spot right here. And on that spot, the electric field is Q over 4 pi epsilon naught r squared. And it's times the r hat vector, because the r hat vector points radially outward. So again, representing that in purple, that's my electric field vector right there. But we can also draw my dA vector right there. And that's that guy. Notice they're right on the money, exactly the same. So what I'm going to say is I'm going to dot that with dA r hat. Again, notice it points the exact same direction. Okay. Now, technically speaking, I could tell you exactly what that would be, let's say in spherical coordinates. And that would be nice. But to be honest with you, if you ever find yourself working out complicated integrals on this left-hand side of Gauss's law, you've done something horribly, horribly wrong. Okay. So that closed integral of E dot dA, I'm really literally taking the electric field at a particular point and then calculating the dA at that particular point, and then dot producting them at that particular point, and then integrating over all such particular points until I get the total answer. So one thing you need to know about dot products is dot products are linear operators. what that means is basically you can take, let's say, a constant c times a vector a plus a constant d times a vector b, and you can take a dot product of it with a vector e, or with a scalar times the vector c, or let's do a vector symbol instead of a hat symbol, plus f times the vector g, like this. What this means is I can do my distributive property, for instance, and see that I get c times e times a dot c plus c times f times a dot g plus d times e times b times c dot product plus finally d times f times b dotted with g. That's what the linear operator means. Means you could pull out all the constants in front and all that good stuff, which is a lot simpler in this particular one than it is in the example I showed you. So what I'm going to do is I'm going to have q over 4 pi epsilon naught big R squared dA, and then all I have left is r hat dot r hat. I want to remind you that a dot b is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them when they're tail to tail. So notice those two vectors are tail to tail, and that angle's theta. You could also write that as a b cosine theta, because that's the same as saying the magnitude. So can anybody tell me what's the magnitude of the r hat vector? Remember, hat vectors mean something. All right, well, let me give you the answer. So all hat vectors like I hat, j hat, and k hat are exactly 1 unit long. That does not mean 1 meter. That does not mean 1 Newton. That does not mean 1 meter per second. It just means 1. Okay, so according to the formula AB cosine theta, r hat dot r hat should be 1 times the cosine of 0 degrees. And of course, 1 times cosine of 0 degrees is what?
1.
Exactly. So now I can say that part just becomes 1, and I just get, remember, the q is actually evaluated on the surface. That's what makes it the surface integral. You're actually evaluating the arguments on the surface of the circle or the sphere. And in this case, that means out a distance r. So that q is just a constant out in front, and it's 4 pi epsilon naught r squared, or I should say that whole electric field is that. And then I have left just the integral of dA over the sphere. Now remember, the dA is surface area. So really what this is asking is this integral right here is just the surface area of a sphere. So does anybody recall the formula for the surface area of a sphere? I think you were guessing probably right, but in this case, since the sphere has a radius r, it's 4 pi r squared. Okay. So this stuff down here, where I drew all that stuff about dot products, that was sort of like what I'd call a sidebar. So I'm going to draw a line, a black line separating it from everything else. And I'm going to do another one right here. Okay, so that was my little sidebar, if you will. Now I can say finally that the net electric flux over that sphere is Q over 4 pi epsilon naught r squared times 4 pi r squared. And that gives me what? Anybody want to venture a algebraic calculation here?
Q over epsilon naught.
Exactly. And so what I'm showing you here is each of those things canceled out, and all I got was Q over epsilon naught. Now, what I did was calculate the left-hand side of Gauss's law for a very specific and somewhat easily doable problem. Okay. But I did that, even though it's not technically a proof and not a derivation, I did that because all of them will give the right answer. And the right answer is this. Here's Gauss's law. You can also write that with 2 S's instead of 1 if you'd like. But Gauss's law basically says the closed integral of E dot dA is equal to Q enclosed, and that means the total charge enclosed within the Gaussian surface divided by epsilon naught. So I pseudo derived it, but that really is what the Gauss's law is and what we call integral form. In this class, we mostly use Gauss's law in integral form to solve for the E. In other words, we use it to solve for the electric field. Now, I told you earlier, it's Gauss's law, not Gauss's helpful hint that sometimes works. That's what I mean. Gauss's law is always true, but unless you have very specific symmetries, you cannot use Gauss's law to solve for the electric field like I'm getting ready to do. Okay, so that's key to understand. You should probably write that down unless certain symmetries exist, then we cannot use Gauss to solve for the E field. That doesn't mean it's not true anymore. It just means we can't solve it that way. In fact, in a more robust or a more mature or more higher level course of electricity and magnetism, you predominantly don't use the integral form of Gauss's law at all. You use the differential equation form, and you can solve all sorts of problems with it. So it's extremely valuable. Okay, so let me show you an example. Example 1. Imagine an infinitely long straight uh non-conducting. Yes, somebody asked me something. with a uniform charge density of lambda. So in other words, we're solving that very first problem that we solved using the integral form of Coulomb's law. We're going to solve that same problem now with Gauss's law. Okay, so we have I'm going to imagine an infinitely long, and I said non-conducting just because if it's non-conducting, then the charges will stay right where they are. Whereas if it's a conducting wire, if I create an electric field, the charges will move all around because of the existing electric field, crazy stuff like that. So I wanted you to think in terms of conductors versus non-conductors and what they do. So let's go ahead and draw our coordinate system again. So here's my coordinate system. What I am going to do is I'm going to say this right here is my x-axis, and I'm going to say this right here is my y-axis, and I'm going to imagine a very, very, crap, a very, very thin but long wire like that. And this wire, of course, goes on for infinity that way and for infinity that way. Okay. And I am going to imagine, actually, I've drawn it too close to this edge. I just remembered why I didn't want to draw it that close to the edge. Let me see if I can. Okay, I'm going to draw it over here. Okay, so that's good enough. And I'm going to say I want to know the electric field strength at a distance r from the wire. Okay. Does everybody understand that question and everything? Now, here's what we're going to do. We know Gauss's law. So this is our solution. Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Okay. I want to guess a Gaussian surface where everywhere on that surface, the electric field will, one, be constant in strength, and two, perpendicular to that surface. Or other parts of the surface, for instance, if you made it something instead of smooth like a sphere, you could make it like a soup can or a box or something like that. Different surfaces might have different angles with respect to the electric field. So the other option is if it's not the electric field strength is a constant on the surface and perpendicular to the surface, and the other option is the electric field is actually going to be perpendicular to the surface. Okay, perpendicular to the surface vector that we've been talking about is really what we're saying here. So can anybody imagine a surface that will have the electric field strength on it due to this charge carrying wire, have that field strength be a constant on that surface? Anyone? Okay. I'm going to go ahead and do it. And what I'm going to tell you is that if I made a cylinder then you'd see the electric field at the point on the x-axis clearly points to the right. And if I drew a cylinder like this, a vector perpendicular to the surface would also have dA pointing to the right. Now, I also have to do a cylinder that's concentric with the existing wire. So if I don't do that, I would have obviously some issues. So I'm going to come over to here and say that that's the other side of the cylinder. Now, it is technically a cylinder, but it also has to be a closed surface. So I can't just say it's a cylinder. It's got to be a cylinder with a top and a bottom. Okay. So you can imagine a toilet paper roll with a cap on each end, or you can imagine a soup can. Okay. The reason being is, for instance, if we, even using cylindrical coordinates, which would be ideal for this particular shape, you could say that a little surface area element would be this little surface area element right here. Okay. That would be my little differential area element. That would be dA. Okay. And the electric field, of course, would be pointing that way as well. So you see, at least on the soup label portion, the electric field should be a constant on the soup label, and it should be perpendicular to the surface. Once you go up to the top, things are a little different. So for instance, I could say, again, using cylindrical coordinates, this right here would be a typical area element in cylindrical coordinates. So I should have drawn these in green too, since it was of the actual Gaussian surface. So now I'm doing it because my brain won't let me not do it. Okay. So in this case, the dA, I'll call dA sub t for the top. And of course, something similar would exist. Dang it. Something similar would exist for the bottom, like this. Only again, our rule is that the dA vectors point from the inside out, or at least in a direction consistent with the inside out. So I'm going to call this one over here dA SL for soup label, the top one dA top, and the bottom one dA bottom. Okay. Now, unlike a lot of equations that we use in physics, Gauss's law is one where we work the left-hand side and we work the right-hand side almost simultaneously. Then we set them equal to each other, and then we solve it for the thing that we want. So this is the way that I think is most or least confusing and most helpful. So the first thing I'm going to do is I'm going to compute the left-hand side of Gauss's law. So I'll write left-hand side. But in order for me to do that, I'm first going to make a hypothesis. So my hypothesis is, given that I've used Coulomb's law so much and I understand how electric fields behave for given charge distributions, then I make the argument that the electric field is in fact equal to a magnitude that depends only on r, the distance away from the wire. And I'm going to say that it points radially outward. So I'm going to put an r hat next to it, and I'm going to put a subscript c on that, because this r hat is not the same as the r hat from spherical coordinates. Spherical coordinates has all the vectors. You take any point in space, whether it's in the XY plane or above the XY plane or below the XY plane, you take any point in space and you draw a line from the origin to that point, then the r hat vector would be parallel to that line pointing away from the origin. In cylindrical coordinates, what you have to do is imagine all the points in space, but first start off with the ones that are in the XY plane and take all the points in the XY plane and draw a line from the origin to that point. That's the direction of r hat. Okay. And that's r hat sub c for cylindrical coordinates. Now, if you happen to have points above the XY plane, you're still going to do the same thing, except you're not going to go back to the origin. You're just going to go to the z axis at the same height that your point is. So you'd see that the r in cylindrical coordinates doesn't have a k component. It doesn't have a z component. So that's why I put the subscript c on there. So my hypothesis is that the electric field is dependent on the distance away, r, and only the distance away, r, and it points radially outward according to cylindrical coordinates, okay? So with that, I can now write the closed integral of E dot dA is actually going to be an integral over the top plus an integral over the soup label plus an integral over the bottom. In other words, it's a closed surface. And remember that circle on the integral is totally meant for us to use that as a memory device to say, hey, I can't do this unless I'm dealing with a closed surface. So I've got to take into account the top, the bottom, and the soup label. Okay. So the integral over the top is going to be basically the same electric field that I said, which is E of R RC hat, but the dA is actually going to be some dA K hat because it points upward. Does everybody see how that's the case? Then there's going to be an integral. I'm doing a different order. I'm going to do the bottom first. And in this case, again, I get E of R, which, by the way, E of R is definitely not a constant on the top or the bottom because the R's vary. So I can't even say that E of R is a constant in this case. But the dot dA in this case is going to be negative dA K hat. And then finally, over the soup label, that's going to be E of R RC dotted with, again, I'm just going to write as dA. There are things that you could work out to make what dA is, but I'm telling you, if you're integrating the left-hand side of Gauss's law, you're doing it wrong, okay? At least if you're using it to try to find the electric field. In this case, the dA is multiplied by RC hat as well. So what I can do is take my integral over the top, and the dot product's still a linear operator, so I can still write E of R dA, and then I can write RC dotted with dotted with K hat. And remember what I told you about the cylindrical coordinates R vector, their R hat vector has no K components. So they are purely perpendicular, which means the answer for this guy is going to be 1 times 1 times the cosine of 90 degrees, which is 0. We can go on and say, remember there had a minus in the bottom in the integral for the bottom. So I'm going to put the minus out in front. I'm again going to say E of R dA. This time I'm going to say RC dotted with K hat. And of course, we remember that was a negative K hat, but that's where the negative came from. And again, for this one, we can see that this dot product is going to give us 0. I probably could have fit the soup label in there, but I don't want to. So when we actually do the integral on the soup label portion of the Gaussian surface, in that case, the electric field's an actual constant. It's been evaluated at R equal R, which is the radius of the cylinder. So I can pull it out in front and say E of R times the integral. Now all I have is dA, but I have a RC dotted with RC. And of course, you guys know that is 1 times cosine of 0, which is 1. So this whole thing is 1. And all we get is the integral over the soup label. Now, I didn't draw this earlier, and I really should have, but I'm going to say the height of the soup can is L. So if I were to, let's say, cut the soup label down along that line, I would lay it out and it would make a what shape? Anyone? If I took the soup label off of a soup can and I cut it so that I could make it one flat strip and I laid it out, what shape would it make?
A rectangle?
A rectangle, exactly. And given what I've told you about this one, what would be the height and width of the soup label rectangle? Could you tell me, for instance, what the width is?
Circumference.
Exactly. It's the circumference. So that's 2 pi r. And then what's this height?
Height.
Yeah, I called it L in the diagram. But that's all. The area of that soup label is what that integral is. So I'm going to say equals E of R times 2 pi r times L. Does everybody see that that's what it should be? So I've now got the left-hand side done. Now I want to do the right-hand side. Now the right-hand side is the area where you occasionally might have to do an integral or something like that. I'll remind you, for instance, that Q enclosed could be the integral of lambda dl, or the integral of sigma dA, or the integral of rho dV. In this case, we don't have to worry too much about it. We've got a fairly simple, hopefully you can see that we have a fairly simple calculation to do. Can anybody tell me how much charge is enclosed inside of that Gaussian surface? And I've been using this phrase. Let me go ahead and label that this is called a Gaussian surface. Okay. So read the original problem. It says, imagine an infinitely long, straight, non-conducting wire with a uniform charge density of lambda. That's like coulombs per meter. What is E at a distance R from the charged wire? I'll also give you this little hint. That quantity is a constant. No one can guess how much charge is enclosed in that cylinder of radius R and height L? So when the charge density, which could be either lambda, sigma, or rho, like I've drawn down there, when that's a constant, then the charge is just lambda times the length, or sigma times the area, or rho times the volume. Now, can someone tell me what Q enclosed would be? Anyone? All right, well, it's just lambda times L, and then of course we had the epsilon naught in the formula. Now I'm going to say left-hand side equals right-hand side. And when I do that, I get E of R times 2 pi RL is equal to lambda L over epsilon naught. And I think you can see now that the L's cancel out. And using my hypothesis, where I actually stated what it would be, I can now say that E, the electric field, is equal to lambda over 2 pi epsilon naught R in the RC direction, which is essentially the same thing as the I direction when it's drawn like this, but I could turn the coordinate system by any number of degrees, and then it would be an I again, and again, and again, and again. Well, that's the definition of the radial vector from cylindrical coordinates. So notice we did get exactly the same result as we got when we integrated Coulomb's law. Remember that was dE is equal to dQ RP minus RdQ over 4 pi epsilon naught RP minus RdQ to the third power. So using that formula, we got exactly the same thing, but I would argue that was a lot harder than doing it this way. Anybody have any questions on that? All right, I'm going to have a lot of time to do a lot more of these. And I've got to teach you the nuts and bolts of doing an actual surface integral, which I've sort of hinted at here, but I haven't really done one. You can, of course, look at the ones that I've done on my YouTube channel. Just do surface integral, do a search for surface integral, or maybe just the word surface, and you'd probably find it. But I have plenty of time for that. What I'm going to do now is I'm going to imagine a very, very, very large plate uniformly charged. In other words, every square centimeter, square millimeter, or square inch, whatever you want to use, if you took a square inch and found that it had 3 coulombs in it, then every other square inch would have 3 coulombs in it. So I'm going to start off again with a coordinate system. I'm going to draw my coordinate system right here, and I'm going to do it with the fancy drawing techniques. Okay. So there's my z-axis. And this is my x-axis in principle. Okay. So now I'm going to say this is x, this is y, this is z. I'm going to imagine an infinitely large plane. What did I do? I went over 6. So 1, 2, 3, 4, 5, 6. I'm going to go roughly to there. Now, I'm just showing you a small part of it, but what I'm saying is this goes on for infinity that direction, that direction, that direction, that direction, that direction, and that direction. Okay, so it's infinitely large. I'm going to say it has a charge per unit area sigma. Okay, now since it's infinitely large, if you considered, for instance, let's just look at a small spot right here. So imagine this is a line on the actual plate that I just drew, and I got this positive charge right here. Now, if this particular positive charge were to cause an electric field, you would expect it to cause an electric field that would point straight up there, but over here it would point that way, and over here it would point that way. But notice right here, you're going to have another charge, and that would tend to cause this one to point that way. And this one might even cause this one to point this way. So you'd see that this guy would cancel out with that guy. So what I'm saying is, if you think about the symmetry of it, you would expect that the electric field, due to this particular plate, would actually point up. Since it's a positively charged, it would point up above the plane and it would point down below the plane. Okay. So I'm going to say hypothesis E is equal to E of Z X Y K hat for Z greater than 0, and E of Z X Y with a negative in front of it, K hat, for Z less than 0. That's my hypothesis. Okay. There's the question, what is E? So I'm going to choose a Gaussian surface. This time I'm going to choose a Gaussian surface that basically would be parallel to the plane, because that appears, based on the K hat, that appears to be what would happen. So I will say that's the top of my Gaussian surface. I would also say that this Gaussian surface runs down into the plane and then goes past the plane, and of course has a bottom too. So it's the same Gaussian surface we did before, just the parts that are important are going to be different in this one. Okay. So again, we got these little guys for dA top and dA bottom. And again, we have this little guy for dA soup label. Okay. But you can see I'm saying my electric field is going to point in the K hat direction. So the soup label is not going to matter at all in this case, because the dA soup label is going to consistently be perpendicular to the electric field. What we do know is the closed integral of E dot dA is supposed to be Q enclosed over epsilon naught Now remember, this is uniformly distributed. So uniformly distributed means that sigma is a constant. So now I'm going to do my left-hand side. The left-hand side is going to be the closed integral of E dot dA. But that's going to be the integral over the top plus the integral over the soup label plus the integral over the bottom, which I'm going to say integral over the top is going to be E of, Well, actually, I'm going to leave off the arguments in this case because it's so much, but I was showing you that I'm not making any assumptions that the electric field is only going to depend on Z. In fact, I'm allowing it to depend on Z and X and Y. I'm just going to call it E K hat for the top. And then, of course, that's going to be dotted with dA K hat for the top plus the integral. Now, in this case, the electric field is going to be plus or minus because for Z greater than 0, it's going to be positive, and for Z less than 0, it's going to be negative. So I'm going to say plus or minus E K hat dotted with dA. In this case, it's going to be RC hat. And then I'm going to say the integral, that was over the soup label. Now I'm going to say the integral over the bottom, and that's going to be negative E K hat. Notice the negative there. Dotted with negative dA K hat, because that's the way that one's pointing. So with all this, I end up getting the integral. Notice if I evaluate it on the top, it seems that I can't argue that E would depend on anything other than Z. And in fact, it looks like I'm evaluating it at Z. So I'm going to actually change what I wrote there. I'm going to go ahead and pull that electric field out in front, and I'm just going to say E of Z integral dA K hat dot K hat, which I think you all can see is, of course, 1. Now I'm going to say plus, in this case, it's the integral of plus or minus E dA K hat dot RC, which is the same thing we had before, and we got 0 then, so we're going to get 0 now. And that was over the soup label. God damn it. And now I'm going to say minus a minus gives me a positive. So I'm going to say positive over the bottom. Actually, no, I don't want to do that yet. I want to pull out the E first. So I'm going to pull out E being a function of Z only, integral over the bottom of dA K hat dot K hat, which again is going to give me 1. And if I take the liberty of calling this little area of the circle that's on the top, the circle that's on the bottom, and the circle that's in the middle, then I can go ahead and say that this turns out being E of Z times A plus 0 plus E of Z times A, which is just 2E of Z times A. Now I'm going a little bit over, so y'all are welcome to leave if you need to. I'm just going to finish this last step, which is the right-hand side, and then setting them equal to each other. So right-hand side is Q enclosed over epsilon naught. Like I said, it's uniformly distributed though, so Q enclosed is just sigma times A. So now I say left-hand side equals right-hand side. And with that one, I get 2 E of Z A is equal to sigma A over epsilon naught, or finally, using our hypothesis, I get E is equal to sigma over 2 epsilon naught K hat for Z greater than 0, and negative sigma over 2 epsilon naught K hat for Z less than 0. And that's the answer. All right, you guys are free to go. Make sure you send me a message in the chat so I have your first and last name for roll. but you are free to go, and I'll wait for the last person to leave in case anybody has any questions. You've got a good start here. You definitely should remember to complete chapter 4 homework this weekend and complete the test. You have a test that's due Sunday. Actually, for you guys, I think it's due Monday. So make sure you get your test done. Also, chapter 4 homework's due. Chapter 5 is not due, but you can definitely start it now. I've given you a good intro to a lot of stuff here. There's a lot more problems for me to solve, but you've got a lot of them that you can see on my YouTube channel too. Not a problem, Reynolds. You're welcome to, and we can make a breakout room if there's more than one person around. You can also chat it to me. That's private. Darnisha, do you have any questions? Or Carly, do you have any questions? I saw I did see your message, Carly. In fact, let me
you
look.
did.
Yes. Yeah,
Okay, thank you.
yeah, I've been swamped. I haven't had a chance to do anything, but I did see that you wrote back. So I'll get
You're
back
fine,
with
I
you
get
tonight.
it. Okay, thank you.
Thank you. Sorry about that, Carly.
Okay.
All right, Reynolds, let me stop recording. Because if you want it private, it definitely gonna be private if I recorded it all. All right, I'm